The data link layer protocols we will cover next. The TCP/IP network access layer is the equivalent of two of the OSI layers, layer 1 and 2, the data link layer and the physical layer. We've already discussed the physical layer, so now let's discuss the data link layer. As shown in the figure to your right, the data link layer is responsible for the exchange of frames between nodes over physical network media, and it allows the upper layers to access the media and control how data is placed and received on the media. One thing to point out is that in layer 2 notation for network devices connected to a common medium is called a node. Specifically, the data link layer performs these two basic services. It accepts layer 3 packets and packages them into data units called frames, and it controls the media access control and performs error detection. Error detection is important. The data link layer effectively separates the media transitions that occur as the packet is forwarded from the communication processes of the higher layers, and the data link layer receives packets from and directs the packets to an upper layer protocol, in this case IPv4 or IPv6. And these upper layer protocol does not need to be aware of which media the communication will use. It doesn't care which media that you use. It doesn't affect it. As we discuss things in this book and in this chapter, media and medium do not refer to digital content and multimedia such as audio, animation, and television or video. Instead, it refers to the type of material that actually carries the data signal, such as our copper that we've already discussed about, as well as our fiber optics. The data link layer is actually divided into two sublayers. You have the logical link control and you have the media access control. The logical link control is your upper level of the sublayer, and it defines the software processes that provide services to the network layer protocols. It places information in the frame that identifies which network layer protocol is being used for the frame. And this information allows multiple layer 3 protocols such as our IPv4 and IPv6 to utilize the same network interface and media. For the media access control, it is the lower of the sublayer that defines the media access processes performed by the hardware, and it provides the data link layer addressing and delimiting of data according to the physical signaling requirements of the medium and the type of data link layer protocol is used. When we separate the data link layer into sublayer, it allows for one type of frame defined by the upper layer to access different types of media defined by the lower layer. Such is the case in many LAN technologies, including Ethernet. The figure to the right illustrates how the data link layer is separated into the LLC and to the MAC sublayer. So you see those two delimited out. The MAC sublayer also communicates with the wireless technologies such as Wi-Fi and Bluetooth to send and receive frames wirelessly. So we have our Ethernet, we also have our Wi-Fi, and we have our Bluetooth. Layer 2 protocols specify the encapsulation of the packet into a frame and the techniques for getting the encapsulated packet on and off each medium. Each medium adds its own bit of information, so it needs to know which type of media it is covering. A packet travels from source host to destination host. They typically go across several different types of media throughout the different networks that they go through to get from one end to the other. So this addressing is very important. Without the data link layer, network layer protocols such as IP would have to make provisions for connecting to every type of media that could exist along the delivery path. Also, IP would have to adapt every time a new network technology or medium was developed. And the process would hamper your protocol, it would slow things down, and it also hampers the media innovation and development. And it's a key reason for using a layered approach to networking. This animation to the right will provide an example of a PC that's in Paris trying to connect to a laptop in Japan, and you'll see how the packets change with the addressing as it goes through the different types of media. You go from your LAN to your wireless and satellite, and then back down again to the laptop. So let's watch this right quick. It goes from the PC to the router, then that frame is going out to the satellite, and then it's coming back to the wireless router and going wirelessly to your laptop. You can always click on this More button to get more information about what has occurred in case you need additional points as you're reading. Different media access control methods may be required during the course of a single communication, and each network environment that packets encounter as they travel from a local host, here's our local host, to a remote host can have different characteristics. For example, the LAN consists of many hosts connecting to access the network medium on an ad hoc basis. Several links consist of a direct connection between only two devices, over which data flows sequentially as bits in an orderly way. Your router interface encapsulates the packet into the appropriate frame, and a suitable media access control method is used to access each link. In any given exchange of network layer packets, there's numerous data link layer and media transitions. At each hop along the path, a router accepts a frame from a medium, it de-encapsulates the frame, it re-encapsulates the packet into a new frame, and then forwards it to the new frame to the appropriate medium on the segment of the physical network. So the router is looking at it each time, trying to decide where it goes, and it addresses the frame at each location. Here's an example. It goes with a LAN header and transfer and trailer to the router. Then we get a WAN header and a WAN trailer. And then once it would go from that router to its next destination, the header and trailer would also change. Your data link layer prepares your packet for transport across the local media by encapsulating it with the header and the trailer to create a frame. So you'll see here we have the frame header, we have the packet, the segment, and the data, and then we have the trailer. The data link layer protocols require control information to enable the protocol to function correctly. And the control information typically answers which node are in the communication with each other, when does the communication between individual nodes begin and when does it end, and which errors occur while the nodes communicate. And then finally, which nodes will communicate next. Unlike our other PDUs that have been discussed in this course, the data link layer frame includes your header, and that contains control information such as addressing and is located in the beginning of the PDU. That's your frame header. Then you have your data, and that contains the IP header, the transport layer header, and the application data. And finally we have the trailer, and that contains control information for error detection added to the end of the PDU. Let's look a little bit more at the layer 2 frame structure. When your data travels on the media, it's converted into a stream of bits, or ones and zeros. If a node is receiving long streams of bits, how does it determine where a frame starts and stops and which bits represent the address? Your framing breaks the stream into decipherable groupings with control information inserted in the header and trailer as values in different fields. And this format gives your physical signals a structure that can be received by nodes and decoded into packets at their destination. You have your frame start and stop indicator flags, and these are used by the MAC sublayer to identify the beginning and the end limits of the frame. So here we have our frame start, we have our frame stop, so that it knows when this particular frame has begun and ended. Then you have your addressing, and that's used by the MAC sublayer to identify the source and destination nodes. So here we have the addressing, and it tells it where it came from and where it's going to. Then you have the type. This is used by the LLC to identify the layer 3 protocol. Then you have a control that identifies the special flow control services. Finally, we have our data, and this contains the frame payload or the packet header, segment header, and the data. And then we have error detection, and this is included after the data to form the trailer, and these frame fields are used in error detection. Not all protocols include all these fields, and the standards for a specific data link protocol is defined by the actual frame formatting. You have activity 1. This is where you can go through and put in information where you believe things are to go, and you can just drag and drop the information in and check your information and see how things look. And you can just drag them around however you need for them to be. And then you would just, play with them, see what you get right, see what you get wrong. If you get things wrong, you can drag them out and decide that you want to go about it a different way. You can check what you've done there, and you just keep going until you find everything right. It's a good learning tool. Just like with the other topics we've covered, there are standards involved with the data link layer. Unlike the protocols in the upper layers of the TCP/IP suite, the data link layer protocols are generally not defined by requests for comments or RFCs, although the IEEE and the Engineering Task Force maintains the functional protocols and services for TCP/IP protocol in the upper layers. Specifically, the data link layer services and specifications are defined by multiple standards based on a variety of technologies and media to which the protocols are applied. And some of these standards are integrated both at layer 1 and layer 2 services. The functional protocols and services at the data link layer are described by engineering organizations which set up public and open standards and protocols, and communication companies which set up and use proprietary protocols to take advantage of new advances in technology or market opportunities. Some of these engineering organizations, like I said, are the IEEE. You have the International Telecommunications Union and the ISO. You also will have the American National Standards Institute. And the figure to your right gives you some examples. We have the standard organization, IEEE, and the standards that they're set forth. Here we have another activity. This is based on these standards and which organization handles the standards. Next we'll cover topologies. It's great if you know where the computers are and how things are set up, and once you get into network management, part of your job may be to set up the topology. and how things are going to work. Regulating the placement of data frames into the media is controlled by the media access control sublayer. And the media access control is the equivalent of traffic rules that regulate the entrance of motor vehicles onto a highway. So what we're going to do now with the topology is we're going to regulate how frames are going across our network. There are different ways to regulate placing the frames onto the media, and the protocols at the data link layer define the rules for access to different media. Some media access control methods use highly controlled processes to ensure that frames are safely placed on the media. These methods are defined by sophisticated protocols, which require mechanisms that introduce overhead into the network. Among the different implementations of the data link layer protocols, there's different methods of controlling access to the media. And these media access control techniques define if and how the nodes share the media. The actual media access control method used depends on the topology, how the connections between the nodes appears in the data link layer, and media sharing, how the nodes share the media. The media sharing can be point-to-point, such as in a WAN connection, or shared, such as in a LAN network. The topology of a network is the arrangement of the relationship of the network devices and the interconnections between them. The LAN and WAN topologies can be viewed in two different ways. So basically, where are your computers and how are they set up? You have your physical topology, and that refers to the physical connections and identifies how end devices and infrastructure devices such as routers, switches, and wireless access points are interconnected. And physical topologies are usually point-to-point or star, and we'll get more into that in a bit. Here we have our physical topology, and you can see where they are located, each device. Then you have your logical topology, and it refers to the way a network transfers frames from one node to the next. And these arrangements consist of virtual connections between the nodes of a network. The data link layer sees the logical topology of a network when controlling data access to the media, and if the logical topology that influences the type of network framing and media across media access control that's going to be used. Here we have point-to-point topology. This is hub and spoke. This is considered full mesh. A little bit more about those. WANs are commonly interconnected using the following physical topologies. You have point-to-point, and this is the simplest topology, which consists of a permanent link between two endpoints. For this reason, this is very popular in WAN topology. Next, we have our hub and spoke, and it's a WAN version of the star topology in which a central site interconnects branches, the branch sites using point-to-point links. So here we have our hub, and then we have our different spokes coming from that hub. Then you have mesh, and this is topology provides high availability, but it requires that every end system be interconnected to every other system. Therefore, the administrative and physical costs can be high, and each link is essentially a point-to-point link to the other nodes. And variations of this topology include a partial mesh, where some but not all of the endpoints are interconnected. So these are the three common physical WAN topologies that are illustrated here. Here is our point-to-point topology. We have node 1, and it's connected to node 2. So it's limited to our two nodes. In this arrangement, the two nodes do not have to share the media with other hosts. In addition, the node does not have to make any determination about whether an incoming frame is destined for it or another node. because there's only the 2 points. The logical data link protocols can be very simple, as all frames on the media can only travel to or from the 2 nodes, and the frames are placed on the media by the node at the end and taken off the media by the node at the other end. So it comes onto the network here, travels, comes off here, or vice versa. The data link layer protocols could provide more sophisticated media access control processes for logical point-to-point topologies, but this would only add unnecessary protocol overhead, and the more overhead you add, the slower your packets travel. The end nodes communicating in a point-to-point network can be physically connected via a number of intermediate devices. However, the use of physical devices in the network does not affect the logical topology. As we see here in Figure 1, the source and destination node may be indirectly connected to each other over some geographical distances, and in some cases the logical connection between your nodes forms what's called a virtual circuit. So here we have our source node and our destination node, and they're traveling across the network, and this is considered a logical point-to-point connection. A virtual circuit is a logical connection created within a network between 2 network devices, and the 2 nodes of either end of the virtual circuit exchange the frames with each other. This occurs even if the frames are directed through intermediary devices. Your virtual circuits are important logical communication constructs used by some of the Layer 2 technologies. The media access method used for the data link protocol is determined by the logical point-to-point topology, not the physical one. So here's our logical topology. Here is the physical devices in between the routers. So here you see the source node, the destination node, and we see a cloud. Here we see the source node, we have a switch, we have a router. This may be a hub or a multi-layer switch. Then it comes back out and we're coming back to our other router. With our WAN topologies, we can either have half duplex communication or full duplex communication. So here in Figure 1 we show you a point-to-point topology. And in this point-to-point network, data can flow in one of 2 ways, either half duplex or full duplex. Half duplex means that both devices can transmit and receive on the media, but cannot do so simultaneously. So if this device is sending information, this device has to wait. Here's an example. They had to take turns. In full duplex communication, both devices can transmit and receive on the media at the exact same time, and the data link layer assumes that the media is available for transmission for both nodes at any time, so that no media arbitration is necessary in the data link layer. So here is full duplex. Our physical topology defines how the end systems are physically interconnected, and in a shared media LANs, end devices can be interconnected using some of the following physical topologies. We have our star topology. As you can see, it looks like a star. The end devices are connected to a central intermediate device. Our early star topologies interconnected end devices using a hub. However, hubs are very chatty. The star topologies now use switches, And the star topology is the most common physical LAN topology, primarily because it's easy to install, it's very scalable, and it's easy to troubleshoot. Then you can have your extended star or your hybrid. Here you see we've got two stars, and these two are connected. Okay, therefore it's extended. You have your bus topology, and this is where all systems are chained to each other and terminated in some way on each end. The infrastructure devices such as switches are not required to interconnect the end devices, and the bus topology was used in legacy Ethernet networks because it was inexpensive to use and easy to set up. All you had to do is run your cable and make sure you had terminators at wherever the endpoint was. Then you have your ring system, that's this one, and that end systems are connected to their respective neighbor, forming a ring. And unlike the bus topology, the ring does not need to be terminated because they're all interconnected in a big circle. Ring topologies were used in legacy fiber distributed data interface networks. Specifically, they employ a second ring for fault tolerance or performance enhancements. Okay, so these two are legacy, and these two are more widely used today. The logical topologies of a network is closely related to the mechanisms used to manage the network access. Access methods provide the procedure to manage our network access so that all of our stations have access. It doesn't do any good to have them on your network if they can't access the network. When several entities share the same media, some mechanisms must be in place to control the access. And the access methods are applied to the network to regulate the media access. So you have to have rules in place for them to use the same media. Some network topologies share a common medium with multiple nodes. At one time, there may be a number of devices attempting to send and receive data using the network media. And there are rules that govern how these devices share the media. Who gets to go first, who sends what. And there are two basic types. You have your contention-based access and your controlled access. With your contention-based access, all the nodes compete for the use of the medium, but have a plan if there are collisions. Here is an example. It says, I'll try to send when I am ready. Here says, I'll try to send when I am ready, and so will he. So they all try to send when things are ready. Then you have control access, and each node has its own time to use the medium. He says, I have a packet to send, but it's not my turn. I will wait. He said, it's my turn to send. I will send now. And this one has nothing. So they take turns. The data link protocol specifies the media access control method that will provide the appropriate balance between frame control, frame protection, and network overhead. If there's too much overhead going on with your network slows down. Continuing with our LAN topologies, when using a non-deterministic contention-based method, a network device can attempt to access the medium whenever it has data to send. And to prevent the complete chaos on the media, these methods use a carrier sense multiple access process to first detect if the media is carrying a signal. Basically, it's listening to see if anything is busy. If a carrier signal on the media from another node is detected, it means that another device is transmitting, so the line is busy, so it has to wait its turn. It is possible that the CSMA process will fail and two devices will transmit at the same time, creating a data collision. If this occurs, the data sent by both devices will be corrupted and will need to be resent. Contention-based media access control methods do not have the overhead of controlled access method, and a mechanism for tracking whose turn it is to access the media is not required. However, The contention-based systems do not scale well under heavy media use. As use and the number of nodes increase, the probability of successful access without a collision decreases. So basically, the more crowded it gets, the more apt you are to bump into each other. Same with your packets on a network. The CSMA is usually implemented in conjunction with a method of resolving the media contention, and there's two of those. You have carrier sense multiple access with collision detection, or carrier sense multiple access with collision avoidance. With collision detection, the end device monitors the media for the presence of a data signal. If the data signal is absent and therefore the media is free, the device transmits the data. If the signals are then detected that show another device was transmitting at the same time, all devices stop sending and try again later. Traditional forms of Ethernet use this method. Then you have your carrier sense multiple access with avoidance. The end device examines the media for presence of a data signal. If the media is free, the device sends a notification across the media of its intent to use. Basically, it's saying, I'm getting ready to send something so that everybody knows this. Once it receives a clearance to transmit, the device then sends the data. This method is used by the 802.11 wireless networking technologies. So it's a good idea to know which contention-based technology is used with which type of characteristics. You will see this again. A logical multi-access topology enables a number of nodes to communicate by using the same shared media, and data from only one node can be placed on the medium at any given time. Every node sees all the frames that are on the medium, but only the node in which the frame is addressed processes the content of the frame. Having many nodes share access to the medium requires a data link media access control method to regulate the transmission of data and thereby reduce the collision between the different signals. This animation is going to show you how nodes access the media in a multi-access topology. When using the controlled access method, the network device takes turns in sequence to access the medium. If an end device does not need to access the medium, then the opportunity passes to the next end device. And this process is facilitated by the use of a token. An end device acquires the token and places a frame on the media. No other device can do so until the frame has arrived and been processed at the destination when it releases the token. This method is also known as scheduled access or deterministic. In a logical ring topology, each node in turn receives a frame. If the frame is not addressed to the node passes the frame to the next node. And this allows a ring to use a control media access control technique called token passing. So it goes from computer A, and in this example it goes to B, B sees that it doesn't belong to it, so it sends it down the line until it reaches its destination. There are multiple media access control techniques that could be used with a logical ring depending on the level of control required. For example, only one frame at a time is usually carried by the media, and if there's no data being transmitted, a signal known as a token can be placed on the media and the node and only place the data frame and the media when it has the token. Remember that the data link layer sees a logical ring topology. The actual physical cabling topology could be something altogether different. Here you have another activity to help you determine what's physical topology and what's logical topology. Then we have our data link frame. Although there's many different data link layer protocols that describe the data link layer frames, each frame type has three basic parts. It has its header, its data, and its trailer. All data link layer protocols encapsulate the layer 3 PDU, because remember it's coming down through the layers. So layer 3 goes to layer 2. So the layer 3 PDU within the data field of the frame. However, the structure of the frame and the fields contained in the header and trailer vary according to the protocol. Your data link layer protocol describes the features required for the transport of packets across the different media. And these features of the protocol are integrated into the encapsulation of the frame. When the frame arrives at the destination and the data link protocol takes the frame off the media, the framing information is read and discarded. There is no one frame structure that meets the needs of all data transportation across all types of media. So depending on the environment, the amount of control information needed in the frame varies to match the media access control requirements of the media and logical topology. In figure 1 here you see a fragile environment requires more control. However, a protected environment is shown in figure 2 and it requires fewer controls. So this one is considered fragile and this one is considered protected. In a protected environment, we can count on the frame arriving at its destination. Fewer controls are needed, resulting in a smaller field and smaller frames. Here in the fragile environment, more controls are needed to ensure delivery, and the header and the trailer fields are larger as more control information is needed. You see it's going from the router, from the LAN, we're going satellite, and then we're coming back. In our data link layers, the frame header contains the control information specified by the data link layer protocol for the specific logical topology and media used. Here in the header we have the start frame, the address, and the type. Okay, and the type field indicates the upper layer service contained in the frame. The figure to the right displays the Ethernet frame header. The start frame field indicates the beginning of the frame. So here. The source and destination address, again, are in the address, and all of this is inside the header. Different data link layer protocols may use different fields from those mentioned. Another example of layer 2 protocol header and frame fields could include the priority quality of service field, the logical connection control field, the physical link control field, and the flow control field. Also, you could have congestion control field. So you need to make sure familiarize yourself with these because the purpose and function of the data link layer protocols are related to the specific topologies in media. Each protocol has to be examined to gain a detailed understanding of how its frame structured. As protocols are discussed throughout this course, more information about the frame structure will be explained. The data link layer provides addressing that's used in transporting a frame across the shared local media. The device addresses at this layer are referred to as the physical address. The data link layer addressing is contained within the frame header and specifies the frame destination node on the local network. The frame header may also contain the source address of the frame. Unlike Layer 3 logical addresses, which are hierarchical physical addresses, do not indicate on what network the device is located. Instead, the physical address is a unique device-specific address. If the device is moved to another network or subnet, it will still function with the same Layer 2 physical address. An address that is device-specific and non-hierarchical cannot be used to locate a device across large networks or the internet. This would be like trying to find a single house within the entire world with nothing more than a house number and a street name. So your physical address can be used to locate a device within a limited area. Limited. For this reason, the data link address is only used for local delivery. Addresses at this layer have no meaning beyond the local network. Compare that to a Layer 3, where the address in the packet header are carried from source host to destination host regardless of the number of network hops along the route. If the data must pass onto another network segment, an intermediate device, such as a router, is necessary. The router must accept the frame based on the physical address, de-encapsulate the frame in order to examine the hierarchical address or IP address. Then, using the IP address, the router is able to determine the network location of the destination device and the best path to reach it. Once it knows where to forward the packet, the router then creates a new frame for the packet, and the new frame is sent to the next segment toward its final destination. So it de-encapsulates, then it re-encapsulates and sends it on. Our data link layer protocols add a trailer to the end of each frame. So we had our header, now we have a trailer. And this process is called error detection and is accomplished by placing a logical or mathematical summary of the bits that comprise the frame in the trailer. Error detection is added at the data link layer because the signals on the media could be subject to interference, distortion, or loss that would substantially change the bit values that those signals represent. A transmitting node creates a logical summary of the contents of the frame, and this is known as cyclical redundancy check, and the value is placed on the frame check sequence field of the frame to represent the contents of the frame. If you click here and here, you can get additional information. The TCP/IP network, all OSI Layer 2 protocols work with the IP at OSI Layer 3. However, the actual Layer 2 protocol used depends on the logical topology of the network and the implementation of the physical layer. Given the wide range of physical media used across the range of topologies in networking, there are correspondingly high number of Layer 2 protocols in use. Each protocol performs media access control for specified Layer 2 logical topologies. This means that a number of different network devices can act as nodes that operate at the data link layer when implementing those protocols. These devices include the network adapter or network interface card. Remember, that's called the NIC that's inside your computer. The network interface card, or 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 network interface as well as the interface on routers and layer 2 switches. Our layer 2 protocol used for a particular network topology is determined by the technology used to implement that topology. And the technology determines the size of the network, which then in terms of the number of hosts and geographic scope and the services to be provided over the network. Your LAN typically uses a high bandwidth technology that's capable of supporting large number of hosts, and a LAN's relatively small geographic area, a single building or a multi-building campus, and its high density of users make these technologies more cost effective. However, using high bandwidth technology is usually not cost effective for WANs that cover large geographic areas like cities or multiple cities, and the cost of the long distance physical links and the technology used to carry the signals over those distances typically results in lower bandwidth capability. Some common data link layer protocols include Ethernet, point-to-point protocol, which is PPP, or 802.11, which is wireless. Here's an example of the layer 2 protocols. We go from wireless, then we did the point-to-point protocol, go HDLC, that's yet another protocol, then we're going to use frame relay, then Ethernet frame, all the way to the end. The Ethernet is a dominant LAN technology. It's family of networking technologies that are defined in the IEEE as 802.2 and 802.3. And the standards define both layer 2 protocols and layer 1 technologies. Ethernet is the most widely used LAN technology and supports data bandwidths of 10 megabits, 100 megabits, or 1 gigabit, or 10 gigabit. The basic frame format of the IEEE sublayers of the OSI layer 1 and 2 remain consistent across all forms of Ethernet. However, the methods of detecting and placing data on the media vary with different implementations, so it depends on how you implement this. The Ethernet provides an unacknowledged connectionless service over a shared media using CSMA-CD as the media access method. Its shared media requires that the Ethernet frame header use a data link layer to address to identify the source and destination nodes. As the most LAN protocols, this address is referred to as the MAC address of the node, and Ethernet MAC address is 48 bits and is generally represented in hexadecimal format. The figure shows the many fields of an Ethernet frame. At the data link layer, the frame structure is nearly identical for all speeds of Ethernet. However, at your physical layer, different versions of Ethernet place the bits onto the media differently, and the Ethernet is discussed in more detail in the next chapter. Point-to-point protocol is another data link layer protocol, and it is used to deliver frames between two nodes. Unlike many of the data link layer protocols that are defined by electrical engineering organizations, PPP standards is defined by RFCs, and it was developed as a WAN protocol and remains the protocol of choice to implement many serial WANs. PPP can be used on various physical media, including twisted pair, fiber optic, and satellite transmission, as well as for virtual connections. It uses a layered architecture, and to accommodate the different types of media, it establishes logical connections, called sessions, between two nodes. These sessions hides the underlying physical media from the upper protocol, and these sessions also provide a method for encapsulating multiple protocols over a point-to-point link. Each protocol encapsulates over the link establishes its own PPP session. It's also the two nodes to negotiate options within the PPP sessions. This includes authentication, compression, and multi-link. And here is an example of what all is included within that frame. You have 802. Finally, we have the 802.11 wireless. That's the IEEE standard that uses the same 802.11 LLC and 48-bit addressing scheme as other 802 LANs. However, there are many differences at the MAC sublayer and physical layer. In a wireless environment, it requires special consideration. There is no definable physical connectivity. Therefore, external factors may interfere with data transfer, and it's difficult to control access. To meet these challenges, wireless standards have additional controls. The 802.11 standard is commonly referred to as Wi-Fi, and it's contention-based system, and it uses a CSMA-CA media access process. The collision avoidance specifies a random back-off procedure for all nodes that are waiting to transmit. And the most likely opportunity for medium contention is just after the medium becomes available. Making the nodes back off for a random period greatly reduces the likelihood of a collision, so not everyone is waiting the same amount of time, they're waiting different intervals. The 802.11 networks also use data link acknowledgments to confirm that a frame is received successfully. If the sending station does not detect the acknowledgement frame, either because the original data frame or the acknowledgement was not received intact, the frame is retransmitted. The explicit acknowledgement overcomes interference and other radio-related problems. Other services supported by the 802.11 are authentication, association, and privacy. As you'll see in the figure to the right, the 802.11 frame contains the following fields. There's protocol version field, and you have version 802.11 frame in use. Then you see type and subtype field. This identifies one of three functions and subfunctions of the frame, either control, data, or management. Then you have 2DS field. It's a set to 1 in data frames destined for the distribution system. From DS field, set to 1 in the data frames exiting the distribution system. Then you have more fragments field. That's set to 1 for frames that have another fragment. You have retry field. It's set to 1 if the frame is a retransmission of an earlier frame. You have power management field. It's set to 1 to indicate that a node will be in power save mode. You have more data field. It's set to 1 to indicate a node in power save mode, that more frames are buffered for that mode. You have wired equivalency privacy. That's WEP field. It's set to 1 if the frame contains WEP encrypted information for security. You have order field. It's set to 1 in a data field frame that uses strictly ordered service class, and it does not need reordering. You have duration ID field. It's depending on the type of frame, represents either the time in microseconds required to transmit the frame or an association identity for the station that transmitted the frame. Next we have destination address field. That's the MAC address of the final destination node in the network. You have your source address field. That's your MAC address of the node that initiated the frame. You have receiver address field. That's your MAC address that identifies the wireless device that is the immediate recipient of the frame. You have fragment number field that indicates the number of each fragment of a frame. You have sequence number field that indicates the sequence number assigned to the frame. Transmitted frames are identified by duplicate sequence numbers. You have transmitter address field, that's the MAC address that identifies the wireless device that transmitted the frame. You have frame body field that contains the information being transported for data frames, typically an IP packet. And then you have the FCS field, and it contains a 32-bit cycle redundancy check of the frame. Finally, we have another activity that you can practice going through the frames. Here's an Ethernet frame. You have a PPP frame, and then you have the wireless frame. All of those are good points for you to go through. So we have, to sum it up, we've gone through our physical layer and our data link layer. And you need to make sure that you understand these, complete the labs that have been assigned, and also you'll want to make sure you've completed all your packet tracers.